Hi, and welcome to this video on GeMRTOS, a generic and embedded multiprocessor real-time operating system. In this video, you will learn about the control blocks and code structure of the GeMRTOS, which make it flexible and adaptable for modern embedded real-time applications. GeMRTOS is a generic, embedded, multiprocessor, real-time, event-driven operating system. GeMRTOS categorizes events into three kinds. Timed events. These events happen when system time reaches a previously scheduled occurrence time. External events. These events are produced by peripherals and are usually related to interrupt service routines. Internal events. These events occur when specific conditions are met during runtime. Internal events include system exceptions and internal signals. The GeMRTOS controller handles timed events and external events, generating the corresponding interrupt requests. All the system status is preserved in control blocks that are highly interconnected. Events change the system status and consequently the control block information and the links among them are modified accordingly. The following control blocks are defined by GeMRTOS. The kernel control block, which centralizes the system's information. The task control block contains information about a system task. The event control blocks are created for each possible event during runtime. The scheduling list control blocks are used for the GeMRTOS hybrid partition scheduling. The processor control blocks are used to keep track of each system processor's status. The resource control blocks are responsible for implementing various system resources such as semaphores or message queues. During runtime, the signal control blocks are used to define internal exceptions. All of these control blocks are highly interconnected in order to maintain the system's runtime status. The event time linked list supports timed events. The occurrence time of each event control block is used to sort them. The GeMRTOS controller implements system time internally, removing the need for a timer interrupt. The GeMRTOS controller compares the current system time to the closest occurrence time. If the system time is greater than or equal to the occurrence time of the first event control block, the GeMRTOS controller's interrupt module sends a processor interrupt. Timed interrupts are thus supported by inserting an event control block into the event time list. The interrupt service routine will handle the event based on its type. Various types can be defined, including periodic task release, task deadlines, and timeouts, among others. The resource control blocks help with resource management. Two main lists are defined by the resource control blocks. The resource waiting list, in which event control blocks are sorted based on the priority of the resource request. Events can be associated with semaphore requests, message senders, or data producers, among others, depending on the type of resource. The granted list is the other main resource list. This list connects the events associated with semaphore grants, message receivers, or data consumers, depending on the type of the resource. It is possible to create as many resource control blocks as needed. Scheduling lists are used to manage task and subsystem scheduling. The scheduling list defines two main linked lists. The task ready list, which sorts task control blocks based on the ready priority assigned to each task. And the running list, which sorts the task control blocks based on the execution priority assigned to each task. Of course, task preemption occurs if the lowest execution priority is lower than the highest ready priority. There may be as many scheduling lists as the designer sees fit. Task control blocks associated with tasks that are neither ready nor running are linked to the task waiting list. Depending on the status of the tasks and events, task control blocks are linked to their associated event control blocks. For example, a periodic running task may grant a resource, and such a resource may have a timeout event configured to avoid causing a resource blockade. The task's associated event list links all of these control blocks. A waiting task, on the other hand, may be waiting for a resource with a specific request timeout. As a result, the information held in the control blocks and how they are linked among them determine the state of a task and the system status. The system status determines the tasks that have to be executed. The processor with the identification number 1 performs system initialization during system boot. The processor with the identification number 1 then executes the user initialization defined in the program's main function. The user tasks and scheduling lists are created and configured in the main function. The GeMRTOS is then started, and the remaining processors are integrated into the system runtime. The GeMRTOS begins a cycle of execution starting with the task start or resume function. This function selects the next task to run based on the hybrid partition scheduling strategy. All the GeMRTOS functions are executed in the critical section by grading the GeMRTOS controller's mutex. When user tasks, interrupt service, routines, idle tasks, or signal codes are being executed, 3 main actions may occur. First, an external interrupt produced by either a timed or an external event. The interrupt handler routine determines the event type by reading the GeMRTOS controller register. Second, the code invokes a system call. System calls are executed in the critical section and have the potential to change the system's status. Or, third, the task finishes its execution, and then the processor becomes available to execute another task. After an interruption, the system status is changed accordingly, and then a new task is started or resumed. The system calls may return to finish the task, or they may suspend it and then start or resume another task. The same happens when a task is completed. It should be noted that, because the system's flow is well defined, the system's behavior will be determined by the data in the control blocks and how the control blocks are linked. For example, let's consider a period task. When this type of task is created, the task code, task stack, period, and initial time offset must all be specified. The task can be created during runtime from any other user task or at the main function. The task creation will generate a timed event with an occurrence time equal to the specified initial offset. A new waiting task is created as a result of the task creation. After a while, the time event causes a system interrupt, and the interrupt handler routine is executed. Because it is a periodic task, a new timed event is linked into the time list in the interrupt routine, with the occurrence time incremented with the task period. By linking the task control block to the ready list of its respective scheduling list, the task state is changed. At this point, one of 2 things could happen. The task completes its execution and must be restarted to be ready for the next invocation. Its task control block is linked to the waiting list, or the timed event occurs, and the task is not completed before the next release. When the time event occurs, the timed event is relinked with the updated occurrence time. If the task is not completed before the next period, it can be aborted by re-initializing it, or a signal can be issued to execute a pre-configured signal routine. As previously stated, several behaviors and task and event types can be defined to cover various kinds of runtime characteristics. In this manner, it was briefly described how GeMRTOS handles events. Different types of tasks and events can be included by defining the data store into the control blocks and how they are linked when events occur. Furthermore, different types of tasks, events, resources, and signals are independent of the rest of the tasks, events, resources, and signals defined. As a result, and due to the generic nature of the GeMRTOS, new defined types may coexist with either native or pre-defined types. GeMRTOS is a groundbreaking innovation for embedded real-time systems. The Intel Neos 2 processor was used in its implementation, but the source code is available for porting to other processor architectures. Information is available on GitHub and the GeMRTOS website. Please contact us at GeMRTOS.com for more information or if you want to join us in contributing to the project. Thank you for your time.